In this video, we're going to take a look here at example 3 and 4 out of this section, and we're going to be doing something that's going to be pretty remarkable. We would like to prove that the function e to the x is equal to its Maclaurin series, not some of the time, but all of the time. Again, if I was to go ahead here and try to think about let me go ahead and try to draw out some nice shapes here. But if I was to go ahead and think about what this is really saying, this is saying that if I was to go ahead and take a look at this graph of e to the x as my f of x, and if I was to draw the entire Maclaurin series, remember that would be the series that starts at 0 and goes to infinity with a bunch of stuff. So this is the infinitely long polynomial thing. I want to prove that that blue polynomial isn't close to being the black thing, but it actually is the black thing, that those things are identical, not just for some x's, but for all x's. Okay, this is really crazy. To be able to show this is a really, really difficult thing to do, especially because all that we know so far is that if I was to sketch this polynomial, again, Maclaurin centered here, I know that at any individual value of n that I stop at, so if I again choose a degree that's not an infinite thing for a polynomial here, but I go up to maybe say n from 0 to 10, I'm going to start to see again these gaps that begin to occur at certain spots. And what we had said in the previous several videos is that the only way I could guarantee that this blue thing and black function are identical is if the gaps disappeared. And if I want to show that these things are the same always, I would need to show that every gap disappears. So we're going to see how we can do that here, and I'll start with stating at least our goal. We want to show that when I let the degree of my polynomial go to infinity, my remainder at every possible x turns into 0. That is, all those red gaps turn into 0. So, okay, let's see how we might be able to do this. So I'll start by saying this. How about we deal with one x at a time? But since I don't want to deal with a specific x just yet, let's let x be some real number. Okay? I'm just going to let x be some number. Maybe let's just say it's right here on the number line. Okay? There's my x value. That's the one I'm going to work with. And I'm going to figure out what happens to the gap above it. Okay. Well, automatically, what I want to do is if I'm interested in using Taylor's theorem to help me, is I'm going to need an interval that I can put around this particular x. Now, I think it's always easy to get an interval that's around this x and also includes our starting point of x0. Because I think that you can always find a value that is going to be bigger than x, and then if you just take that value and grab its negative, you certainly contain 0. So I'm going to call this value d and negative d. Okay, x definitely is in there, and so is our value of 0. So here's what I'll be able to say. I'll say there must exist a number d such that the absolute value of x is less than or equal to d. That is, x is in between d and negative d. Okay? So we have that nice little interval there. So now we will apply Taylor's theorem. Okay, so here's how we do this. Let's see. First, we note that f of x equaling e to the x is, again, infinitely differentiable at x naught, which is equal to 0. right? Definitely is going to meet that condition. We can also then see that on this interval from negative d to d, we see that the absolute value of our n plus first derivative of our function, again, should just be the same as just e to the x. When absolute value, that does nothing. And we're interested on that interval, what is this going to be less than or equal to? Well, again, if you kind of imagine like drawing up some vertical bars here, and only thinking about the function in between or on this green interval, if I only look between the green bars, I can see that the black function, the biggest that it could actually ever be, is going to be over here on this right side. And so the largest value that I ever get out of this is certainly e to the d. And I can claim that as my value of m. Okay, so this becomes really powerful. So we can say that we can see that this is definitely going to hold. So by Taylor's theorem, if I do the remainder of n at this value of x, my remainder is going to be less than or equal to my value of m over my n plus 1 factorial, x minus my x naught, which is 0, to n plus 1. So there's not a whole lot I can actually do with this at the moment, but I can go ahead and state that this is true for all x that exist in the interval negative d to d. Okay. Now, again, our goal here is to try to show that the remainders will all disappear. And right now what we have with Taylor's theorem is a bound on how big those remainders might be. We know the remainder is, at biggest, this value, whatever the heck that value is. But notice that since my remainder is actually being absolute valued, another thing that I could state is that my remainder is also greater than or equal to 0. And this becomes a perfect time to take advantage of something that we haven't used for a very long time. Notice, if I want the limit of my remainder to be equal to 0, and I have my remainder wedged between two functions, can you think about a cool property of limits that I might be able to apply so I can figure out what the thing squeezed in the middle might be able to equal when I slap a limit on it? Well, if you're thinking the squeeze theorem, you're absolutely right. Yeah, we could use the squeeze theorem here. Notice that the limit of 0 as n approaches infinity is clearly equal to 0. And also, if I do the limit as n approaches 0 of the other side, so that's my e to the d over n plus 1 factorial, and then notice I have x to the n plus 1th power, I'm going to have to simplify that down a little bit. This is the hard limit. But if I can show it's 0, then I know the limit of the inside thing is 0. Now I'm going to go ahead and pull a move here where I'm going to take this e to the d and pull it out to the front. Notice it doesn't have any n's in it, so it's just a number and I can move it outside. And what I'm going to be left with is this. And here's where all of a sudden something really important is going to come back. A long time ago, back in section 5.1.2, we introduced a limit. In fact, right now I would ask you, go to your 5.1.2 notes and take a look at the last example that we did in that section. Pause the video if you need to, but take a look at the last example we did in that section, and I'd like you to compare the limit there to the limit that we have here, and see if you can guess what the answer to this limit is going to be. Well, if you took a look back at your notes, what you may have found is that this limit is definitely equal to 0. I'll put in here C5.1.2. This is amazing because now we can say that by the squeeze theorem, the limit as n approaches infinity of the absolute value of r sub n of x has to be equal to 0. Is that what we wanted to show? Well, sort of. We almost wanted to show that. We kind of have right now the limit of the absolute value of something is equal to 0. We just wanted, though, the limit of just the regular thing to be equal to 0. But notice that that's actually not a problem, because if we go back to what we covered in 5.1.1, that very first section of chapter 5, we saw that if the limit of the absolute value of a sequence was equal to 0, then the limit all by itself would be equal to 0. So I can go ahead and say here that this implies that the limit r sub n of x must be equal to 0 all by itself. Notice, though, what we've shown here then is that the remainders, these red gaps, will actually completely disappear on the interval negative d to d. But notice, wasn't d just kind of an arbitrarily selected value? Right? It was just something that was bigger. So could I pick d to be a billion? Sure. Could I pick it to be a trillion? Yeah. Could I pick it to be a trillion to the trillionth power? Well, of course. So ultimately, since there's no bound on d, since d has no upper bound, it can be arbitrarily large. And so we can say that the limit as n approaches infinity of r sub n of x will be equal to 0 on negative infinity to infinity. That is, it works for all x. But if the remainder is equal to 0 all the time, then that means that e to the x must be identical to its Maclaurin series. Notice the statement here is not that these things are roughly the same, but that they are a perfect 100% match. This should be mind-blowing. E to the x is a terrible function. It's so complicated. It's so messy. But what we find is that it's actually identical to a super long polynomial thing. If you're having trouble seeing it again, keep in mind that this is just the polynomial 1 plus x plus a half x squared plus 1 over 3 factorial x to the third plus like on and on and on. That polynomial is e to the x. And we got ourselves a little square. The last thing that we can take a look at then in this section is really what are some of the implications here? Really we're saying that this is true, again, on the interval negative infinity to infinity, that these things always match. So if we assume that x is a 1, then that would mean that e to the first power is not roughly the same as plugging a 1 into this thing, but it is identically the same. That is, they are a perfect 100% match. The value of e is the exact same thing as adding together all of these different fractions. This is the value of e. It's not a way to approximate e. If you go forever, it is the value of e. So this is actually just crazy. If you want e to as many decimal places as you want, just keep typing out this series and you will get the value of e. This is a really, really huge result. It's a really, really interesting one as well. We actually have the ability then to do this, not just with some values, but with all values. Hey, do you want to know what e to the 0.5 is? Easy. Just plug 0.5 in for x and you will get a string of numbers that all add up to be exactly e to the 0.5. Hey, you want to know what e to the 7/3 is? You can do that too. You want to know what e to the pi is? We have something to do that as well. So note that using a partial sum of this series, if you only added some of these things, that would allow you to estimate the value of e. But if the infinite series is used, that produces the exact value of e. This is an unbelievably surprising result, and it's really, really cool. The worksheets will ask you to go ahead and try to practice reiterating all these different types of questions. You can see here we've worked through a bunch of different kinds of things over the past couple videos, and those things will be repeated in the worksheets. If we were in a face-to-face class at this point in the semester, I would have been asking you to try to go ahead and spend some time working through example number 5 on your own. And so I'm going to ask you to try to go ahead and work through this and consult the solutions online. I'm not going to go ahead and go through this in the video. I would ask that you try to do this. It's the same thing, just dealing with a different function. Here we had a sine function and a big polynomial that modeled it. And so I'm going to ask you, can you go ahead and try to work through the exact same set of steps to try to understand how we could do something like what we did up here with e to the x, just with a brand new function. Of course, if you have questions, feel free to shoot me an email or visit me during office hours.